Yeah, good. All right. So what I'm showing you here is this special problem that I asked you to do for Monday. There's two things for Monday. There's the heating nitrogen and the adiabatic expansion special problem. I posted a video that has the derivation. The analogous derivation to the one I did last time, which was for an adiabatic reversible expansion. The derivation is for an adiabatic constant pressure expansion, and it's on YouTube on the channel that we've been using. It's on Blackboard. I'm never going to really ask you to derive it because you can just copy it from the video. So I don't really see a point in that, but you may want to take a look at it anyway. And it leads to this equation right here, equation 2, for the final temperature for an adiabatic expansion. At constant pressure. This is the one for reversible. Okay, so how do you solve this problem? Well, once you have the T2, so you get T2 for each of these, you can get them from this equation. So once you have T2, you can get the delta U from that using the equations I told you about last time. You can get delta H. You can get Q and W. Q is 0 because it's adiabatic. That's what it means. And W would then be equal to the change in internal energy because Q is 0. But what I want to tell you is the other thing you have to do is to sketch the PV diagram for each case and compare the amount of work done. Okay, so what this graph is going to look like, at least for the adiabatic reversible case, is you're going to start at a higher temperature, and you'll have a P, a V, and a T, and you're going to move from one isotherm to another. So this is a lower temperature. So you'll end up, if this is your final pressure, you won't go along this isotherm. That would be an isothermal expansion. You would actually go from one isotherm to another. And you'll end up at a certain volume, V2. Now, the final pressure will be 0.1 atmospheres, which is the same for the constant pressure in the adiabatic case. But because the temperature will be different, the final volume will be different. So this is different from what we did with the isothermal constant pressure and the isothermal reversible. In those two cases, we had the same initial state and we had the same final state. That's not the case for the adiabatic because, like I just said, if the pressure is 0.1 atmospheres at the end, but you're at a different temperature, you're going to end up at a different volume. So you're going to have to calculate what those final temperatures are. And of course, that's what you're going to do using these equations here. Let's see. And what you will find is that the T2 for the adiabatic constant pressure case is actually greater, that the temperature doesn't go down as much. Well, the reason for that is because less work is done in the constant pressure case, which does compare quite well to the isothermal case. It's like you have that constant value of the pressure. You don't have the area underneath one of these curves. Now, while the area underneath this adiabat is not as much as would be underneath the isotherm, it's still more than if you had just a constant amount here. So, so what you have to do is I would like you to calculate as well as the T2 for each one. You'll have to calculate V2 for both cases. And to make it easy for you to illustrate the amount of work on a graph, I've given you, I've posted on Blackboard with the special problem, 3 different isotherms, right? This is the isotherm at 298. This is the isotherm that corresponds to the T2 for the constant pressure case. And this is the isotherm that corresponds to the T2 for the adiabatic case. So when this expansion starts, you'll be at a pressure of 1 atmosphere. That pressure is going to go down to 0.1. This says 0.1 here. It's not too, it's fine. And you start at a V1, which I'm not giving you here. It's not written down there, but you can calculate it. Oh, I do want to point out that the bottom of this axis is a little bit faded. I don't know why. But the bottom is not this blue line. That blue line is showing you the final pressure. Okay, so so when you show the area, be sure you go down to this line here. So basically the expansion starts here, it ends at 0.1, and for the adiabatic case, with adiabatic reversible, it'll go down to a lower temperature. So it'll actually go down to here. You'll have to calculate what this final volume is. And what I would like you to do is draw that adiabat from here to here. In other words, draw that line, that very steep, that steeper line that goes from one of these curves to the other, and show the area under that curve. What you're gonna need to do for constant pressure, the constant pressure is constant, so that's easy. But you're going to have to find the final volume here. The final volume, V2, adiabatic constant pressure, is a lot larger than it is for the reversible. Reversible is right here, constant pressure is right there. Well, why is that? Well, you have a higher temperature at the end of that expansion. That's because less work is done, okay? And work is definitely directly related to the change in temperature, because remember, delta U is equal to the work. So when you find the area here is going to be very easy to show, okay? But you're going to have to get the right volume. And then I would really like it if you also did this. What this is showing is, well, what you could use this graph to show is it has the isotherm over here where you start, okay? And if you calculate the final volume, V2, if it was isothermal, in other words, if T1 is equal to T2 is equal to 298, you should be able to calculate that. And then you could show the area under the isotherm as well. So I think if I gave you these 3 curves, they're on Blackboard under the special problem adiabatic expansion. You should be able to picture pretty nicely the different values of the work, because these are the actual isotherms. I mean, I plotted them on Excel, and you know, they're accurate. They're not just something I drew in. Okay, so I hope that helps you finish that, do that special problem. There's lots of things to fill in, all these different values, but really it's T2 for each of these. That's the big deal. T1 is for 298 for both. And then these other things are, you know, not that difficult once you've done that. And I think giving you these graphs, it'll be easy for you to plot what I would like you to show. Okay. So we're actually moving through chapter 2. So we've done quite a bit, but we have quite a bit more to do. We're essentially up to section 2.7, which is thermochemistry. So some of the stuff we're going to cover starting now should be a little more familiar to you than, you know, how is delta U related to delta H and things like that, and these expansions that you never saw before in another course. So we're really finally up to the chemistry part of the course. We're up to heats of reaction, and of course, physical transformation, which I've talked a little bit about some of these already. physical transformation, I mean, you know, like going from a liquid to a gas or going from a solid to a liquid. So I'm going to define some of these later on, and it should be really familiar to you. So what I want to do first is give you some more general information on what enthalpy changes depend on. So some of these things are really pretty obvious, and some of these things are not as obvious. So, of course, the first thing that a delta H of a reaction or process would depend on would be, you know, the things involved, the chemicals reacting or changing phase. So, of course, what's going to matter is what's actually going on, what chemicals are happening. But I want to say that this is kind of why I even bother talking about this. And I've said this before, but it's important and I emphasize it. So the greatest contribution to the delta H for a reaction is due to changes in bonds, in the bonds between atoms. This is a very fundamental thing, okay? And, you know, stuff that you've learned already in other courses, breaking bonds requires energy. So it's endothermic. And forming bonds releases. This is very general. And there are lots of things that can play into this and make there be exceptions, but this is really the way it is. And of course, that means it'd be exothermic. So the breaking and forming of bonds, when you go from reactants to products, it's the breaking and forming of bonds. Determines what I would call, you know, the relative stability of the reactants and the products. Okay. All right. So just to take a very simple example, supposing I consider the reaction of hydrogen and oxygen to make water, which I'm going to put as a gas phase now, just because I have my reasons. But anyway, so let's talk about this in terms of bonds. I mean, we all know what happens in this reaction, right? This releases a lot of energy. And some of that you see as a big fireball, right? So, okay, what bonds are being made and what bonds are being broken? So you start out with two H2 molecules. These bond energies are not that high. It doesn't take that much energy to break these HH bonds. I mean, they're okay, they're single bonds, but they're not as strong as if you had larger nuclei. And in the end, you end up with two water molecules. So just drawing them out to emphasize the fact that you are forming 4 bonds, right? Where you had 3 bonds. Now, these 3 bonds on the left side are not the same strength. Like I said, the HH bonds are a lot weaker than the OO double bond. But the fact is you're forming 4 bonds here. And OH bonds are strong. And you're breaking 3 bonds. And even though this is pretty strong, this OO double bond is strong, the fact that you have the weaker HH ones doesn't make up for the fact that there's 4 stronger bonds on the right. So I always will say that forming more and or stronger bonds, and I teach this in freshman chemistry as well. I don't know if people remember it, but forming more and or stronger bonds will produce a negative delta H for the reaction. Okay, if that's fundamentally what's happening. And actually, I'm going to show you later, a little bit later on, not today, how you can calculate the delta H. So you can calculate the delta H of a reaction from bond enthalpies, which are the energies required to break bonds, from bond enthalpies. This doesn't work too well in all situations, which I'll talk about then. Works best in the gas phase and stuff like that, but we'll leave it for later. Okay, so that's the very first thing that's very important in terms of what delta H's for reactions depend on. So the next thing I'd like to bring up is something that we've really already used. So I've kind of assumed it, but I want to say for the record that delta H's depend on amounts of reactants. That if you're producing 1 mole of something versus producing 10 moles of something, that change in enthalpy will differ by a factor of 10. And we've used this already, because remember, I used that delta H per mole multiplied by the number of moles equals the total delta H. So that's, you know, that's saying that if you have more reacting, you're going to have a larger amount of heat released or absorbed. Okay. And you know, even when you're writing equations, so here's the one I had before. Just make sure I wrote it right. I forgot the 2 here. See, that guess, you know, you might have wondered where those 4 bonds came from. Nobody said anything. Come on, you gotta tell me about these things. And then you could look really smart, you know. Anyway, so if I wrote that equation, what is going on here? So if I wrote this equation instead, so if this has a certain delta H for this reaction, and I thought about, okay, what about this one? We use a lot of fractional coefficients in this course. Well, if this has a certain delta H, this has half the delta H. Okay. So, all right, we're going to, you know, here, and also if you reacted twice as much H2, you'd have twice as big a fireball. You'd release twice as much heat. So I think I've got that point across. So number 3 is that these delta H of reactions depend on the states of the reactants and the products, and going and using this same reaction really as a model. If I consider that reaction 1 takes H2, combines it with a half a mole of O2 to give a mole of H2O in the gas phase, and I want to compare that, just leave a space here if you're taking notes, to reaction 2. And reaction 2 is the same except for one thing, and that is that the liquid is formed instead of the gas. So this has a delta H, I'll call delta H1. This has a delta H, I'll call delta H2. And back from when you were a freshman, we wrote these as thermochemical equations. We put a semicolon and then what the delta H was equal to. So which of these, so which reaction, we know they release heat. Which releases more heat? 1 or 2? So what's the answer to that? What's the only difference about these 2 reactions? Here you end up in the liquid, and here you end up in the gas. Which has a lower energy, the liquid or the gas?
Liquid.
That's right. So that means that when you're going to the liquid from, so let's draw the picture here. We have reactants here, and now we have, let me just write this as H2 plus 1/2 O2. These are both gas. And now I end up with H2O gas or H2O liquid. Okay, and I've sort of exaggerated the difference here, but that's all right. So because the liquid is more stable, lower energy, right? Remember, it has all those stabilizing hydrogen bonds. It has a lower energy. So here is, let's see, this is delta H2, and this is delta H1. So they're both negative, but delta H2 is more negative than delta H1 because H2O liquid is lower in energy. Energy has turned into like my signature. It never looks like energy. It's just like, all right. So the question is, how much lower? Well, we know exactly how much lower, actually, because if you go back up here, that's why I left a space, because I like to put in the process of water. Oh, I did this all wrong. Yeah, how do I do that? I'll just do it this way. It's just stupid because I wanted to do going to the gas. Yeah, I guess I could do it this way. All right, this is fine. So this reaction has the negative. This delta H is the negative of the heat of vaporization of water, because the heat of vaporization is going this way, right? That's the delta H, vaporization goes that way. This is the negative of the heat of vaporization. So I would say that delta H, okay, so wait a minute now. I'm probably going to get this all wrong, but delta. So if you go to gas phase and then go from gas to liquid, you've gone to liquid. Okay, that's fine. So so if you see these cancel here, so I can just add up delta H1, I think, and the negative of delta H vaporization, and that gives delta H2. Okay, so that delta H2 plus delta H vape is equal to delta H1. Okay, that's right. Yeah. And that's what I would have gotten if I'd done it the other way, but it doesn't matter. We get to the same result. And so what you can see with this is that the delta H2 and delta H1 are both negative. The heat of vaporization is positive. So this shows you that that delta H1 is not quite as negative as delta H2, because here you have a negative number and you're adding something to get this one. So the magnitude of the delta H2 is going to be greater. Okay. Yeah. Does everyone see that? Even though I didn't do it the most convenient way. Okay. So how much lower is basically by the heat of vaporization. Okay. So what did I just do? I just kind of used something. I just took two equations and I added them up. I basically said, okay, H2 plus 1/2 O2 goes to H2O gas. And then I had gas going to liquid. That is the way I did it, right? Yeah. And I added them up. And so I ended up with H2 plus O2 going to H2O liquid. So what I just did was I added delta H's for a stepwise process. And why does that even work? So this works because delta H is path independent. Doesn't matter if I go straight from here to here, or I go from here to here and then here to here. All that matters is I started and ended at the same place. Because remember, delta H is just H2 minus H1. And that's because an enthalpy is a state function with an exact differential. Okay, so you can always do this. You can always sum up delta H's for individual steps to get the overall delta H. And the other beautiful thing is that if you want to calculate it, you could do the same thing on paper. In fact, most of the time, you would only run a reaction in the most convenient way to run it. You couldn't even, you're not going to form gas and then condense it to liquid. It's just, but you could do it on paper and you could find out what the delta H would be. So a lot of times, you might be able to write a reaction down in steps on paper. You would never do it that way, but who cares? You can just calculate the delta H all the same. And if you remember, this is what you learned about in general chemistry that is called Hess's law, which basically says if a reaction can be broken into steps, the delta H overall is the sum of the delta H's of the steps. Okay, and like I said, it could be done on paper. It doesn't have to be done for real. Okay. All right, so this is very important, and we'll get back to it soon. But I first want to finish the list of what delta H depends on. All right, so I'm going to finish that. I have number 4, and that is conditions. For example, pressure, temperature, things like that. So why is it that a delta H would depend on conditions? Well, first of all, what is enthalpy? It's defined this way. And enthalpy, as you can see, depends on pressure. The pressure is right there, depends explicitly on pressure. But it also depends on pressure through the internal energy. So this is not always 0. Remember we said for an ideal gas that U is a function only of temperature. That means that there is really only one derivative. There's only du dt. And that du dp would equal 0. Maybe I didn't say that, but I'm saying it now. But that's only for gases, okay? And this thing is not always 0, especially for non-gases. And so there is some kind of dependence of H on P because U depends on P. So you could see why it would be true that the enthalpy might depend on pressure. And it certainly does. Also, the enthalpy depends on temperature. Okay. The derivative of H with respect to temperature at constant pressure, that's the heat capacity. So so the slope of how H depends on T is the heat capacity at constant pressure. So it definitely depends on temperature. And also, H is U plus PV. Clearly, this depends on temperature, at least for gases. Okay, because PV is nRT. So there's all kinds of reasons why the enthalpy would depend on temperature. And so therefore, delta H also depends on pressure and temperature. Okay. So that's why we're very careful to specify the pressure and the temperature at which these delta H's are measured and tabulated, okay, or calculated. So that's why we really care about what conditions, numbers for delta H reaction were measured in or correspond to. Which kind of brings me to the idea of what we call standard enthalpies. All the time we talk about the standard enthalpy of this, the standard enthalpy of that. And what does that even mean? Standard enthalpies. So what standard enthalpies are, these are delta H's at 1 bar pressure, so about 1 atmosphere, but a little bit different, with the reactants and the products in, so here we go again, in their standard states. And the temperature is 298 unless otherwise noted. So you can definitely have a standard enthalpy change at 400 Kelvin or, whatever temperature, but you've got to make sure that it's noted, because if it's not noted, you'll assume it's 298. Okay, so but I introduced this other thing in trying to explain what a standard enthalpy is. I introduced this idea of a standard state. So what is a standard state? And this is just where the language just gets a little, it's really a very, very simple meaning. The standard state of any compound or element is, you have a drum roll, is the pure form of that compound or element. At 1 bar pressure, period. So it just means that when we're talking about reactions, we're not talking about something that's 80%, or, we're talking about pure water. Like, for example, the standard state of liquid water at 298 Kelvin is pure liquid water at 298 Kelvin and 1 bar. Okay, so it's a whole lot of words, but what it means is we're assuming we have a, atmospheric pressure, 1 bar, which is very close to 1 atmosphere, and that this stuff is pure. Okay, the standard state of oxygen gas at 500 Kelvin is pure O2 gas at 1 bar and 500 Kelvin. Okay, so that's really it. Okay, that's the big thing of what a standard state is. And we use this symbol to represent a standard enthalpy change. And this little 0 that I've told you before means 1 bar. I may have said 1 atmosphere. I apologize if I did. It means 1 bar pressure and standard states of reactants and products. In other words, everything is pure. And it also refers to 1 mole. And I'm going to talk a little bit later about what I mean by per mole. Okay. Now, if you read in the book in Atkins, the book uses this symbol in a way I find very strange. So it takes a delta H, a standard enthalpy change for a reaction, and it writes it this way. Delta R H0. So the R is for reaction. I understand that, but why does it put the R as a subscript of the delta? I think it's because it's a reaction enthalpy change. I don't know. I honestly will never understand why they want to use notation like that. But a lot of books do this anyway. So for example, it will call the heat of vaporization, it will call it the delta vape H0. But I'm not going to do that. I'm going to use these. I think they're much, they're much nicer. And I can't possibly do this other thing. It's just too weird. Okay, so clearly these delta H0s depends on temperature, or I wouldn't have to specify a temperature. So I'm going to show you an example of how you can calculate a delta H at a different temperature. That's not 298 where you're given the delta H. So delta H0s depend on temperature. And these can be calculated at temperatures other than 298, where those are the values that you're generally given. Okay, so what I'm going to do is I'm going to use Hess's law. Okay, and I'm going to use a stepwise process to do this. So I believe I emailed you this piece of paper. Looks kind of like this. So this is a problem to illustrate the temperature dependence of a heat of reaction. So here's the reaction. It's a familiar reaction to add H2 to acetylene to get ethylene or ethene. And here's the delta H of this reaction at 298 Kelvin. So what I'm going to do, and I don't have to do this in the lab, I just have to do it on paper. I'm going to write down my reaction. Here's my reactants. There's my products. And what I would like is to get this at 350 Kelvin. That's what I want, the delta H0 for this reaction at 350 Kelvin. So what I'm going to do is I'm going to take the reactants here, at least in my mind, and I'm going to cool them to 298 Kelvin. So now this is 350, this is 298, and I have my C2 H2 gas plus H2 at 298 going to C2 H4. Okay, and now I need to heat the products. So you cool the reactants from 350 to 298. I'm going to heat the products from 298 to 350. And you could see that I've created this three-step process. So this is 1, 2, and 3. Okay, so my delta H at 350 is going to be delta H1 plus, and this is delta H0 at 298 plus delta H2. Okay. So all I need to do is find, well, I'm given this, right? That's actually negative 175.0. So this is already, we already have that. So all I need to do is figure out what is the enthalpy change for cooling. And now here is where I would use the stoichiometric coefficients, which here are very boring. for cooling 1 mole of C2H2 and 1 mole of H2 from 350 to 298. Now, the book gives you a complicated formula with something called a delta CP, which, I find that when I use that formula, I lose sight of which way this is going, whether I'm heating or cooling, and I want to keep track so that I can make sure my signs are right. So I don't use that formula. I just calculate what it is for each step and add them all together. So delta H1, I'm cooling the reactants from 350 to 298. Here I'm heating products. And so here I'm going to have a delta T. The final minus initial will be negative, right? And here the delta T will be positive. And that's what's going to determine the sign of the contributions of these enthalpy changes, delta H1 and delta H2. So for the delta H1, so that's going to be the number of moles. I'm going to call that N. CP, the heat capacity. So what formula are we using? We're using delta H is NCP delta T. Remember that? And that formula relies on the heat capacity being constant over the temperature range. So that's an assumption made here. And if you worked on that special problem I gave you last time, it's also for Monday on how how heating nitrogen. So how, if you were given a more complicated CP that depends on T, you'd have to take that into account. But, we don't load up too many complicated things in one question. So I'd never do that in a question like this. So this is the number of moles of the C2H2 times CP of C2H2 times the delta T. Okay, and the delta T is going to be 298 minus 350. And then I have to add to that the number of moles of H2 times the CP of H2 times the delta T again, which is the same thing. So this would be, okay, so the N would be 1. This is a stoichiometric coefficient, which unfortunately in this example, they're all 1s. But if they weren't 1s, you'd put in whatever they were. And then the heat capacity for the C2H2 is 43.93 joules per Kelvin mole times, this turns out to be negative 52 Kelvin. And this is 1 mole, so the moles cancel. I end up with, I have to add this one, which is 1 times 28.82 joules per Kelvin mole. And again, negative 52 Kelvin is the delta T. And when you add this up, it's negative 2284.4. I kept extra sig figs here. Minus 1498.6. These are all joules. So that's negative 3782 joules, or negative 3.78 kilojoules. Okay, so that is the delta H1. Yeah. Okay, now I have to calculate the other one. So this was for cooling the reactants. This is for heating products. But there's only one product. That product is C2H4. It's also got a 1 here. These are all 1. So I just need to use the heat capacity, which is given on that piece of paper. Delta H2 is NCP of C2H4 times delta T. But this delta T now is 350 minus 298, or positive 52. So this is just 1 times 43.56. That's moles. Times positive 52. So this is 2265 joules, or 2.3 kilojoules. So now I'm going to add this up. So we had minus 3.8. Yeah, it's really only has 2 sig figs. That's why I'm keeping only 2 sig figs here. Plus negative 175. That was the number we were given for the delta H at 298, plus 2.3. So it's important to keep track of the signs here. But you could see that this is not going to be all that different from what it is at 298, because, you know, the heat capacity, you know, the energy released in cooling these and the energy required in heating the products, it's not all that different. It's different, but it ends up making this be negative 176.5. So there is a 1.5 kilojoule per mole difference. Okay, which is not, you know, earth shattering. So it's a lot of work for 1.5 kilojoules, but that's how you do it. And you can imagine if the temperature were bigger difference, there would be a much bigger delta H difference. So, you know, it's a good thing to know how to do. And I'm sure that there are many situations where scientists would want to know what that really was, to a good precision. Okay, so I think the next thing I'm going to talk about is even more familiar, because I'm really going to go through different definitions of standard enthalpies and things like that. So rather than have you write all this, I gave this out as a handout. So some of these things, you know, I've already talked about. Some of these are in Atkins on page 55 to 60, but these are definitions that, you know, as advanced chemistry students, you should be familiar with. The standard enthalpy or heat of vaporization. Obviously, the enthalpy change for vaporizing 1 mole of pure liquid at a pressure, of course, of 1 bar, hence the little 0 there, okay, for the mole, for the 1 bar. And I didn't say anything here, but this is generally given at the temperature of the phase transition. So this would be at 100 degrees C, or 373 Kelvin. And is it endothermic or exothermic? Well, of course, it requires energy to vaporize, so it's endo. The next one is very similar, except it's going from solid to liquid instead of liquid to gas. Again, it's for melting 1 mole pure, right? That's why it's a standard enthalpy change, and it has a standard pressure of 1 bar, and this would be given at the melting point. Generally, the temperature would be at the melting point. And of course, we could have a heat of sublimation of something. I was just recently read that iodine does not sublime. That's actually a kind of a myth, that it actually melts, that there is liquid. When you do these sublimation experiments, if you look very closely, you'll see liquid present. So I was going to give you the example of iodine, but maybe I should instead give the example of carbon dioxide, because that's definitely sublimation. So this would be endothermic as well, all three of these. And then we have something that I talk a lot about in general chemistry, in Chemistry 104. I don't maybe call it this, I call it the heat of solution. But the standard enthalpy of solution has a slightly different definition than what I talk about and when I teach that class. So if you take 1 mole of a substance and dissolve it, you can't just dissolve it in any amount to get a heat of solution. You actually have to dissolve it in enough solvent so the solute molecules don't interact. So the way to make sure you've done that, which we didn't do, by the way, when we did the enthalpy lab, well, we weren't finding a heat of solution there. Here we were. But anyway, the way to do that is to actually dissolve, is to actually measure that delta H and then see if it changes when you dissolve less and less. So if you start with a lot dissolving and at some point the number doesn't change, the per mole number, then you'll know that you're dilute enough to be considered infinite dilution. So anyway, that's the technical definition. Is this endo or exo? You know, we found that for urea, this is endothermic. For many solids, this is endothermic, but it's not endothermic for all of them. And of course, liquids, they could have positive or negative heats of solution. So it could be either. Okay. And it depends, at least if you're dissolving liquids in liquids, it depends on what the intermolecular forces are between, within a liquid, within another liquid, and then when they come together. This is something we teach in Chem 104. But anyway, that's a standard enthalpy of solution. And then there's some that you've heard of, maybe like ionization energy from general chemistry. It really is an enthalpy. And, it's simply taking the metal, pulling away an electron from it, and leaving the positive ion behind. And it could be, you could have a first ionization. Would be the first ionization enthalpy. So for this process, it would end up being the first ionization enthalpy. But then you could have second and third ionizations as well. First of all, is this endothermic or exothermic? So, you got this nucleus that has pretty large positive charge, and you're trying to take an electron away. And yeah, there's other electrons, but the really big deal is the fact that you have this concentrated positive charge that you're trying to take this electron away from. And that takes energy, right? Because these unlike charges attract. So it basically requires energy to remove the electron. So this is an endothermic process. And as you continue to take away more and more of these electrons, it gets more and more endothermic. So the second ionization energy is more positive than the first. And the third is more positive still. So why is that? Why do these, as you go from first to second to third, it requires more and more energy? Anybody? So you take away that electron, you end up with a positive ion. Now you're trying to take an electron away from a positive ion. So that nucleus that's left behind, it's not shielded nearly as well by electrons. It has one too few. And we would say that the effective nuclear charge increases as more electrons are removed. And And what I would say that I call this Z effective, this is the charge I would say is experienced or felt by the outermost electron. So, you know, if you start out, say, with magnesium, you pull off an electron, it takes a whole bunch of energy. It takes a lot more energy to pull off two. And that's because, like I said, you're pulling it away from a positive charge. And you have a Z effective of that, that second electron, the one that's the outermost one now, is feeling a much stronger nucleus. So it takes more energy. But to take away the third one, now you've got to get into the core, and that's a huge jump in energy. And so anyway, the ionization energy definitely goes up as you pull more and more of these electrons off. So it gets more and more endothermic as you do this. Do they teach you about effective nuclear charge in inorganic chemistry these days? Yeah. Good. And then we have the electron gain affinity. So it's sort of the opposite process. It's really adding an electron to a neutral atom. And it's that endothermic or exothermic. Well, kind of like a similar argument to the one I gave before. You have these electrons around here in a big atom, and you're taking an electron and you're putting it, you know, bringing it close to the nucleus. So usually delta H0 electron gain is negative, but not always. And I remember one time looking in my Gen Chem book at electron affinities, right, which are very closely related to this quantity. And I noticed that there were some blank spaces, and that all the values that they gave were negative. And then I started looking into it, and I discovered that the ones that are blank are the ones that are believed to have positive electron gain enthalpies. And why are they blank was because they couldn't measure them. Because as you can imagine, what you have here is if the delta H is positive instead of negative, or if it were positive in certain cases, let's just say was positive in a certain case, then delta H is positive. And now what is delta S for this reaction? Is it positive or negative? Well, you're going from 2 particles of gas to 1, and we'll learn later, you know, that delta S is negative because you have fewer moles of gas on the right side, right-hand side, okay? So that would mean, since delta G is delta H minus T delta S, this is negative, so this is positive, this is positive. So this is not going to be spontaneous. So that's how I sort of understood it, that if it's negative, you can measure it. If it's positive, they're harder, those numbers are harder to get because they're not going to happen very easily. So that's just my commentary on the electron gain enthalpy. Then we have things like, we have the standard enthalpy of combustion. You can write it one of these 2 different ways. The enthalpy change for combusting 1 mole. So if you took benzene, for example, and you combusted it in pure oxygen to get carbon dioxide and water, at 298 Kelvin, water would be a liquid. So what you would have to do when this is per mole of C6H6, so if you balance this equation, which is 12, 15, you have to put 15 halves in front of the oxygen. So when I say it's the delta H0 combustion, that's per mole of C6H6. So that is what the 1 is, right? whenever we talk about per mole, and I'm going to talk about reactions in general, the next item, we mean per mole of anything that has a coefficient of 1. But when we're combusting, we would start with 1 mole of the thing we're combusting, and we would have to have, whatever coefficients we need for everything else to get this to be a 1. And that's per mole of C6H6. So it would really be per 6 moles of CO2 produced. Okay, or, per 15 halves moles of oxygen that are needed for the reaction, or per 3 moles of liquid water produced. So it's intimately connected, directly connected to the stoichiometry of the reaction. So if I go down here and continue with this thought, this delta H0 reaction, or R, the standard reaction enthalpy, the enthalpy change when reactants in their standard states change to products in their standard states at 1 bar pressure, 298 Kelvin, but it's, per mole. So if I had, here's an example, N2, I love this reaction because it has interesting stoichiometry, 2NH3, and my delta H0 for the reaction. So I'm putting a semicolon, and then I put the delta H of the reaction, minus 92.2 kilojoules per mole. Okay. So what does that mean? Minus 92.2 kilojoules per 1 mole of N2, or per 3 moles of H2, or per 2 moles of NH3. So if you were going to say, okay, I start with, 17, all right, let's make it 18 and 18, 36 grams of H2, that turns out to be 2 moles of H2. And I want to know, well, what is the delta H? I would have to take 2 moles of H2 and use this one. And that will tell me how much heat was released. So this is really something we also teach in general chemistry, but you have to recall this. So it's per mole of anything with a 1 here, and it's per whatever number this is, per 3 moles of H2, per 2 moles of NH3, etc. Okay, and if I wrote this equation forming 1 mole of NH3, so supposing I did this, 1/2 N2 plus 3/2 H2 goes to NH3, then my delta H0 would be half of that. It would be negative 46.11 kilojoules per mole. Okay, so it would be half the amount, and that would be kilojoules per 1/2 mole N2, etc. So I can go on and on like this forever, but I think you get the point. Okay, so a bond dissociation enthalpy, delta H0 bond, refers to breaking that bond. So yeah, this is an average enthalpy change for breaking a specific bond in the gas phase. Yeah, and this is a very curious reaction that's written here. And I would say it's kind of hypothetical, because, for example, you can have a delta H0 bond for a CH bond, but there is no CH molecule to put in an equation like this, right? So what this refers to is kind of an average. These are averages of the energies it takes to break these bonds, which would be for all different molecules that have CHs. So it's only good like this if you have, like NO, right? That's an actual molecule. And then you could get the bond enthalpy would actually be a delta H for a reaction. But anyway, we have these numbers. We basically are able to find what they're equal to based on averages. So for example, if you had a CH bond, would include bond enthalpies of different kinds of CH bonds, like this one and this one. These are not necessarily the same. In fact, they would definitely be a little bit different. So they're averages, but they can be used to estimate enthalpies of reactions. And how would you do that? I'm actually going to talk about this a little later, but the basic idea is you sum up the bond dissociation enthalpies for the bonds that are broken and the bonds that form. And when they're broken, they're positive, they're endothermic. It takes energy to break those bonds. And when they form, you have to count them as negative because it releases energy. So you basically add up all the bonds that are broken and formed, and you multiply the number of bonds by the bond dissociation enthalpy for that particular bond, and do it with, you'll have a large positive number because it's going to be the sum, and you're going to add a pretty large negative number to that. So anyway, we'll do examples of, we'll do this later on. The thing is that this works pretty well in estimating a delta H reaction only in certain cases, right? Only for gas phase reactions. And the reason you could really understand that, and that's because there is no way to include any kind of solute-solvent interactions. The fact that you might have something dissolved that's stabilized by hydrogen bonding or something like that. So, and also if you have reactions with things end up in the liquid, you would have to do something like account for the heat of vaporization, like we did in that first problem with the water, gas, and water liquid. So it works very well in the gas phase, but you start bringing liquids and solutions in, it doesn't work quite as well. So that's that. Now there is another very important delta H, standard delta H, that I call the big one, the biggie. And this is the standard enthalpy of formation. Okay. And this is the enthalpy change when 1 mole of a substance is formed from, and this is the important part, from the stable form of the elements that make it up, okay, at 1 bar pressure and 298 Kelvin. So there's a few different things to talk about here, okay? First of all, what if there is more than one stable form? And we know, like carbon, you can have graphite. Gr is not gaseous, it's graphite. But you could also have diamond. These are both stable. Well, it turns out that this one is a bit more stable. So we use carbon graphite is the stable form of carbon. And here's another aspect of this. So we're talking about taking elements in their stable form and forming any compound. Okay, so the delta H for doing this is the delta H of F0, forming any compound from the elements in the stable form. So what would the delta HF0 be for an element that's in its stable form? So in other words, I'm talking about, let's say we're trying to form iron solid. That's the stable form of iron. The delta HF0 of Fe would be the delta H for the process of taking, this is the stable form of iron, to iron. And of course, that's going to be 0 because you don't do anything to the stable form of iron to get iron solid. You know, you haven't done anything. So this is why the delta HF0s of elements in their stable form is always 0. Okay. And why is this so important? You know, why are delta HF0 such a big deal? And the reason these are a huge deal is because they are well known for many, many, many compounds. And we can combine them using Hess's law to find delta H0 reaction for many reactions. And, you know, you could understand why this would be useful to somebody, you know, working in industry or something, and they want to know, well, how much heat's going to be absorbed or released in this reaction. So I'll show you that next time. But what I wanted to do first was show you a table that I think is pretty interesting. And let me get it here. Here, I like this table. So what I've done here, and I actually show this to my freshmen. I show different substances and some very closely related substances. Okay, and you can notice that you have a lot of zeros on this table. So these are delta HF zeros, and you've got a lot of zeros. And if you look at all those zeros, you see that these are the stable form of the element. Okay, so the delta HF0 of carbon graphite is 0. Same thing for nitrogen gas. Same thing for Cl2 gas, H2 gas. But notice that the delta HF0 for hydrogen atoms is not equal to 0. And notice that it is positive. So what process are we talking about here? The heat of formation that's the standard enthalpy of formation, is the enthalpy change for forming 1 mole of hydrogen atoms, okay, from the elements that comprise it in their stable form, which is H2 gas, 1/2. Okay, so what it's saying is that this delta HF0 is equal to the delta H0 for this process, for this reaction. And hydrogen atoms are less stable than H2 gas. If hydrogen atoms were more stable, then they would be the element in their stable form, but they're not. The stable form is H2. So this process here, to form 1 mole, this is plus 218.0. This requires energy. If you look at oxygen here, it's even more interesting, right? Because we have O, O2, and O3. Only O2 is 0, because going from O2 to O2, the delta H is delta HF0 of O2 is 0. because you're forming the stable form from the stable form. But going to O3 from O2, and now we have to mess with the stoichiometric coefficients here. You always end up with 1 mole of the thing you're forming. So that makes this have to be 3/2 O2 gas. Okay, so this delta H0 for this reaction is positive because this is less stable. It's a less stable form of that element. And of course, it is 142.7 kilojoules per mole. That's the delta HF0 of O3. Okay. And O atoms are even less stable than ozone. So, you know, if I started with O2 and formed 2O, delta H0 for this reaction, actually I better end up with 1 and start with 1/2 because I have to end up with 1 mole of the thing I'm forming. This is delta HF0 of O gas, the delta H for this reaction, and it is uphill because O is less stable than O2 to the tune of 249.2 kilojoules per mole. Okay. So let's write this one. Let's take this ammonium chloride. This is an example. And so what a lot of times, taking a picture here. A lot of times in my freshman class, I'll ask a question like, what reaction has a delta H0 reaction equal to the heat of formation or the delta enthalpy of formation of NH4Cl solid? Okay, so now I'm asking to write a reaction. What are the products of this reaction? 1 mole of NH4Cl is the product in whatever state you're asked to write it in. So what reaction? So now to figure out what's on this side, I have to start with elements in their stable forms. What's the stable form of nitrogen? It's N2. What's the stable form of hydrogen? It's H2. What's the stable form of chlorine? It's Cl2. Okay, so some students in freshman class will write NH4 plus Cl minus. They'll do all kinds of crazy things, but that's wrong. And now what I have to do is I have to say, okay, I have 1 nitrogen here. So that's 1/2 N2. I have 4 hydrogens here. So that's 2 H2. And I have 1 Cl. So that's 1/2 Cl2. So this equation, this chemical equation, has a delta H0 reaction that's equal to the heat of formation of ammonium chloride solid. Okay. And I included one in here. I didn't show the structure of it though. I'll do that next time. All right, I think that's good for today. Kind of done. You have plenty of things to do. How do you feel about this quiz? How are you doing on the quiz? Can I get a little feedback on that? You think you're going to be able to get it done? You know, you could send me an email, you know, if you're having difficulty or, you know, something like that, getting it done. I think it's due Friday at midnight. I can change that by a day if you need it. So let me know. Nobody wants to talk in this class. Nobody wants to tell me anything. You know, I waited online to vote today. It was not just in and out. It took about maybe 20 minutes. Wasn't bad, but anyway. Go vote because we're going to have an epidemic again. It's going to be bad.
Yeah.
Yeah. Anyway. Oh, I want to tell you that Monday after class, we're going to take a little break, and then we're going to have, I would like you to have done that problem 3 as much as you can. And we're going to work on the urea error analysis. If you've already done it and you think you know how to do it, great. You don't really have to come, but I think most of you might need a little help with that. And I'm also going to maybe talk about some of the discussion, what's expected, and also what should go in the summary. If anybody, I don't see Jack here, but if anybody hasn't, so the people who submitted their combustion calculations, I've gotten those back to you, but if you submitted them recently, I haven't looked at them since in the last week or two. So let me know if you submitted them and I didn't look at them yet, because I may forget to do that unless you remind me. Okay. I think for most of you here, I think I've looked at your calculations, all of you. Yeah. Okay. Any question? Corey, you had a question? No. Okay. Anybody else? All right. I'll see you on Monday.
Don't forget that Friday is mole day.
Oh, yeah, right. I actually told my other class that. 10 to the 23rd, man. At 6:02 a.m. on October 23rd. Be there or be square. Oh, all right.
Have a good day.
Bye. Have a nice night.
Hi, thank you, Dr. Cooley.
Thank you. Thanks for listening.
Oh, hi, Dr. Cooley.
Hi, Dina. What's up?
I did the quiz, but like I need, can we go over it today
No,
or?
I can't go over it with you. No, no, no. I mean, if you have a question, I could perhaps give you a hint. Can't go over it with you before it's due. No, I really can't do that.
Okay. I'll take a look at it again and send you email.
All right.
All right. Thank you.
Bye.
Bye.